called computational fluid dynamics. Fancy way of saying what does airflow through this system look like?
All right, here at the track with the Speedin Engineering Evo 5. And what we're doing today is we're playing a little bit with the Speed Engineering products. As you may know, I do a lot of engineering to make sure that these products are as good as possible out of the box. I come from a background, worked on automotive design. I was an engineer on the Acura NSX. I've done rockets. I've done all sorts of fun engineering projects, and playing with cars is the fun part. But what we're doing today is not just having fun in the Evo. What we're also doing is actually punishing these parts. We're beating the ever loving life out of them. So that way I know when I sell that part to you, it's going to work. So we'll start with a couple of things today that we're testing. First and foremost, the most prominent, the induction system. So we're here in Atlanta. It's hot. It's actually kind of a mild day by summer standards, but we're still in the 80s. It's humid, and getting fresh air into an engine when you're hammering on a racetrack is extremely important. So obviously you have the front mount to try to keep the charge cool, but the incoming air is also equally important. So let's take a look at how this is doing. Things that we're trying to test today is watching the IATs, intake air temperature, making sure that we have, cool charge entering the engine. This morning was actually also raining quite a bit. Got pretty soaked. So also a cool thing to check on this particular setup is the water drainage on the box. I know a few people have asked that question on my product and said, hey, well, what happens from the hood scoop when it's pouring rain and there's is it going to cause a problem in my engine? No. The way this is designed is there are drainage holes at the bottom where the filter is, and utilizing the airflow and surface tension, this box is designed to basically pull that water straight to that point, not to your air filter. So that's basically a proof in terms of the IAT today. Definitely keeping the temperatures nice and cool. Also, no issues with water inhalation. So clearly I'm still here. The engine's still running right.
Yeah, and here's a look at what that CFD looks like. That's actually called computational fluid dynamics. Fancy way of saying what does airflow through this system look like? So this is the representation of that. Blue is slow and red is fast. So you can see at the very top there, that intake scoop, and then that goes into the turbo right here. You can just see the acceleration of the air. So it's just a cool way to see that we actually do the engineering behind this to make sure that these products work together as a system. It's not any one component, but how it all flows together. And this shows through those streamlines. It's kind of cool. So you can see how it comes in through the NACA duct in the very top of the hood, goes into the airbox, straight into the turbo.
Next thing we're doing, we're testing some like the high temp material. So a lot of people talk about, hey, can that hood vent, can that cam sensor survive? Like, isn't it just going to melt? The cool thing is some of the thermoplastics that we're using today are so they're awesome. They call them actually, engineered materials, because they can handle the kind of stresses that you wouldn't imagine from plastics in the past. And this is one of the examples right here. This is a cam sensor shield. So as some of the Evo guys know, that cam sensor down there loves to just go bad, to the point that some guys carry around a spare in their glove box. Really annoying. So a shield goes a long way in keeping that heat radiating off the exhaust and the turbo from that cam shield. So this one is specifically designed in a couple key ways. One, it's designed to clear the SAS. This is a supplementary air system. And if you didn't know, on the JDM cars, it's kind of cool. It's actually a factory anti-lag. And once you activate it, it's designed to take the charge air and the throttle body closes and dump it in right before the turbo, and bam, anti-lag. But none of the cam sensors of the market I found could clear this. Now I wanted to keep this system. So we designed a system that does it. Clears the SAS and provides protection for the cam sensor. So this design is really cool in the sense that, I'll also have some vents off the top. A lot of designs I saw were fully encapsulated, and I was kind of worried they'd end up just trapping heat. I mean, we know heat rises, and, if there's not a great ventilation at the top, I kind of worried there'd be some trapping there. Another awesome thing about this material is, versus like the metal heat shields, is the capacity to hold the heat. If I touched any of these metal parts right now, I'd probably burn my hand or melt these gloves immediately, but I can hold this. That's because this material rejects the heat. It does a really great job at keeping that heat away. So it's not just going to sit there and act as like a radiant heat source. Once you get heat soaked in your engine bay, how much protection are you really getting from a metal heat shield? So that's another example here of one of our products that's doing its job, holding up, taking the stress. Now let's talk about another piece we've been playing with, which is our brake ducts. And here today on this track, they have been instrumental. So that's right there, the CP9A. We also make them for the CT9A. So pretty much Evo 4 to 9.
And this is what that CFD looks like for that brake duct. So this is again particle and streamline, showing what the airflow, and you can see that orange is under the car. So it gets a really fresh, cool stream of fast air underneath the car. And then it channels that. And then you can see the channels actually get a little bit smaller. So it works to accelerate that air even more and dump it right onto the back of the rotor. So you're getting a lot of fresh, cool air right into the back of your brakes, right by the caliper, right where you need it to cool down that brake rotor as effectively as possible.
And we've been monitoring that at the track. Our handy little IR gun, point that right in the rotor, and get some measurements. Now, I haven't been on the track, just been kind of chilling between sessions here. So obviously 31C is not very hot. But what we did to do some testing on that was we took the brake duct and we did a session with it open and did a session with it duct taped over. And with the duct taped over, there's no airflow going to the brake duct. It's not going to scoop anything up. And there was a dramatic reduction though. So we'll get to that later. I'll post up a post about exactly what we ended up with on the Delta, but just to give you a peek at it, it was a significant drop in brake fade on the track, as well as huge support in terms of pedal feel by keeping those brakes cool.
Thanks for watching. If you have any questions, comment below, and all the products we talked about are linked in the description.